Okay, so far we have defined what is a residue class map, depending on the place and the residue class field we introduce. And we define evaluation of a function z at P if set in OP, and otherwise we set the image as infinity. And now let me a bit elaborate this structure for the degree 1 places, so the rational places. By the definition, it means that the residue class field is isomorphic to base field K. And in this case, if we apply the definition of the residue class map, we see that for all z in OP, there exists a constant K, A in K, such that the evaluation of set at P is A. And otherwise, again, we set the infinity. And by this evaluation, we can read it as when we have a rational place for all functions in evaluation ring OP, there exists a constant such that z of P is A, or equivalently, if you consider the definition of z of P as z plus A, z plus P, this means that for every function there exists a constant such that this function z minus A has 0 at P. And in the discussion session, we also see that if there is a such that this satisfies this property for all functions in OP, we see that actually this is possible only degree 1 place. And here is uniquely determined by Z. And if you consider degree 1 places, of course, this should be a question we should keep in our minds. I mean, do we have always a rational place in a function field? We still don't know the answer. But at least if K is algebraically close, again, in the discussion session, we will see that all places are rational. And then in this case, we can read an element in F as a function in the sense we consider in this example. So here the points will be the rational places. And if, again in this case, if Z is a function from the full constant field, since it has trivial intersection for all places, for each place, always we will have, let me denote it by A plus B, and the image always be the same. So this is why K tilde is called the full constant field. So there is no constant function outside of K tilde. And similarly, we can also say that K is called a constant field of function field, given function field f. And similarly, this will be the same notation. This is why we call f a function field. However, in the residue class map, we have a general tool. So we may consider evaluation concept at any place. And we still don't know, always do we have degree 1 places. But at least we know that this is an extension. The residue class field is an extension over FQ. So when we apply the residue class map, it will be an extension of K. And now we will see that indeed this is a finite extension. So that means each place has finite degree. So when we consider evaluation of a function z at P, so our image can be in the extension field. And in order to answer the question if degree P is finite, we will prove that for any place in PF and for non-zero transcendental X in P, degree of a place is bounded above by this extension degree, and this is obviously finite because X is transcendental, and this shows us degree P is finite. And in order to prove that, since degree P is defined as the extension degree of the residue class field over K, when we consider n linearly independent elements here over K, this obviously gives us the extension degree. This n is the extension degree. And say Z1 plus P, Z2 plus P. So what I mean is the elements in the residue class field are linearly independent. And here also note that this Zi is from OP because we don't want to work with the infinity. And if we are able to show that, our claims that if these functions from OP are linearly independent over K of X, then we can conclude that this extension degree is bigger than the degree of P. And in order to show that, we show it by contradiction. That means we suppose there exist non-trivial equations, linear combinations of these Zi's with not all zero functions from Q of X, and without loss of generality. We may suppose that we can work with the polynomial coefficients here, and not all divisible by X. This was the trick we used before. And we write these coefficients as the polynomials gi of x times x plus ai. And not all divisible by x means that not all constant terms of phi of x is 0. And here also note that this phi of x is a polynomial. If it is a polynomial, this is also a function, and we may consider its evaluation at P with respect to residue class map. And since we consider x from P, it was our assumption in the statement of this proposition. This belongs to P. So if you consider the evaluation of phi of x at P, that means phi of x plus P. And since this term belongs to P, we can write AIP. So simply, we will define it as AI. And now, with the same logic, if we apply residue class map on this function, because it is also functions, and here 0p denotes the 0 of the residue class field. And in this case, with this observation and by our assumption, we obtain a non-trivial linear combination of z1 plus p up to zn plus zn of p. This is linearly dependent, and this gives us contradiction because we choose these elements as linearly independent. Hence, the degree of P is bounded above the extension degree F over Q of X. So this is all I want to say, and see you at the next lecture. Bye-bye.